guys, and welcome to today's lecture, which is going to be on bonus linear algebra number 6, system of equations. So it's going to be quite simple, and we're going to see how we can solve system of equations using Python. So I'm importing the necessary libraries, NumPy, Matplotlib, the IPython display, and this time I'm importing SymPy, and I will explain to you why it's important. So I'm importing SymPy as sim. I'm going to create my a show function and a showf function. I'm creating this just to show formulas basically. So you just display map x if the x is a formula. So I'm going to create symbols of x, y, and z using sim.symbols, and I give the string basically x, y, z. So we just basically now is allocating them as symbols basically. So let's consider these two formulas, yeah? So y1 equals x divided by 2 multiplied by 2. So maybe just, I mean, of course, like that would be fine as well because the division occurs first, but just for the sake of simplicity, you know. So I'm going to define these two equations. X sub 1 equals x divided, sorry, y sub 1 equals x divided by 2 plus 2. And y sub 2 is minus x plus 4. Okay, so we have these two formulas. And we can use SymPy, you know, to plot these two formulas. But please bear in mind that I can use SymPy.plotting.plot for this objective because I have already allocated x and, you know, y basically to be symbols. Yeah, so just bear that in mind. So if I plot these, I'm going to get, you know, the plots of these two functions basically on the SymPy. Now, obviously, the point at which these two lines intersect is here. So we have a point where x is about, a bit difficult to say, but like around, I would say maybe 2. Sorry, but 1 point, maybe 1.25-ish, yeah, okay. And y is around just over 2.5. Anyway, so if we want to, I mean, like see this, so like it's basically 4 divided by 3 is 1.33, which is around here, and 8 divided by 3, which is about 2.66, which is roughly sort of around this region, okay, just above 2.5. So that's the intersect point between these two lines, which are associated with the two formulas, okay? And I'll put, so I can set the lines intersect. Okay, the lines, of course, associated with the two functions. Now, how do we convert system of equations into a matrix form? Okay, now let's look at these two formulas. So I'm using the showf function that I just showed up there. And remember, I've already created x and y and z to be like symbols. Yeah, hence why I can do that. Now, we have first equation, which is 2x plus 3y minus 4z equals 5, and minus x plus 7y plus 9z equals 7. So in terms of linear algebra, if you were to do this by hand, yeah, you know, we need to understand that, of course, the coefficients are 2, 3, and minus 4 for the first equation, and minus 1, 7, and plus 9 for the second equation. Now we have variables x, y, and z, of course, yeah, and we have two constants, yeah, which are 5 and 7, okay? So that's how this is working at the moment. So this is the formula, okay? Now, how do we do this? Imagine if you want to express this in the form of, you know, using linear algebra language. Yeah, just think about it. So that's our formula here. Just think about it. So if we have a matrix, in the first row, we have 2, 3, minus 4, which are the coefficients of the first formula. And then we have a vertical uh, vector represented by x and y and z. Just think what is going to be the dot product of these two matrices. So if we were to do a dot product, it will be 2x plus 3y plus minus 4 times z, and that would equal to 5. Okay. Well, technically, I mean, if you disregard this bit, we are going to be having, a dot product would produce this row multiplied by elements of this column, element by element. It goes by, like the general dot product format. So 2 times x, 3 times y, minus 4 times z. And from our formula, we know that it's 5. So we can say that that would be equal to 5. So 2x plus 3y minus 4z. And the second row, of course, would lead in the same pattern, basically, would be representing equation 2. Okay? So I want you to think, like, look at those formulas, and if this is new to you, just try to make a sense of it, that how these two formulas can be represented in form of dot product between two matrices. Okay. Now, if you were to do this by hand, if you were to do this by hand, you would be using the reduced row echelon procedure. Yeah. Now, obviously, we are focusing on Python, so we are not going to be doing anything by hand here. But I highly recommend, and I definitely actually recommend, that you go and learn this if you don't know it already. So you need to know what Gaussian elimination and reduced row echelon form are, okay? But just as a reminder, in case you don't know, you have forgotten it. So we basically operate, like procedures and row-wise perform action on the row elements of these matrices so that we can get into a reduced row form, which is that, yeah. Now, as I said, the idea of Gaussian elimination to get a reduced row echelon form of a matrix, you really need to know what it is and how it's done. So, for example, to get from this matrix into this form, we multiply minus 2 of R1, row 1, okay, and we add it to R2. So if we do that, yeah, and then that would replace the row 2. So minus 2 times R1 is going to be minus 2, and it's going to now plus 2. It's going to give us a 0, okay? And again, if we multiply minus 2 by 2, the second element in the first row, and again, adding it to number 4, so minus 2 times 2 is minus 4, adding them, it's going to be 0. So I'm not going to spend time basically going through the manual procedure of performing reduced row echelon form. So you can go through this at your own time, but I highly recommend that you go and learn it, okay? So that you know what it means. So what I would teach you rather here is how are we going to do this procedure using Python, okay? So the idea of a reduced row echelon form is basically that once you have converted your matrix with the constants present, of course, not just the variables, not just the variables, but you have augmented the constants in the matrix as well. If you carry out the Gaussian elimination and get a reduced row echelon form of your matrix, technically, the values that you get on the last column, which are associated with the constants, after you carry out the procedure of Gaussian elimination, is technically going to be your x and your y and your z. So that's how you would go and solve by hand the system of equations if you were to use this method, okay? And once again, I really prefer that if you don't know this, to be going and learning about it. Yeah, there is plenty of resources on YouTube basically on how to do this. So how do we do it in Python? Firstly, we need to use SymPy, so we can't do it with NumPy, yeah? So we cannot do this directly via NumPy. Okay. Now let's look at this function that I've created here, which I'm going to be converting a NumPy array into a SymPy matrix. Yeah. So a NumPy array is basically a NumPy matrix, and we use the sim dot matrix. Yeah. So I'm going to put here using the sim dot matrix function. Okay. So this function takes in a NumPy array here. Okay. It takes a NumPy array and will convert it into the associated matrix. So if we had this as a NumPy array, I mean, like if we look at this at the moment, so if I was to basically show you that, this is our matrix in NumPy form. Okay. So we are using the simpy.matrix function to convert this format, the NumPy array format, into a simpy format matrix. That's all we are doing, okay? So, but obviously at the moment, I haven't allocated it to a name, yeah? So it's just, it ran the operation and gave output, but we want to create it. So we're just gonna repeat this, except that we're gonna allocate it to a name mat.equal, okay? So it's gonna be saved in the memory, okay? Now, let me just show you this first. Now, if we do it like this, you get these other information like the matrix and the, but what I want you to do, okay, is that really you should be doing it in the form of, like just calling the first element in this, output that is coming. So hence why you would use the 0. So how does the function work? So we have a matrix, mat.eq is our name, yeah? Okay, so this is our, let's say, mat.eq is a simpy formatted matrix, yeah? And we are going to use the reduce row echelon form function. But we call this function really, yeah? Remember, we are doing a matrix.rff, yeah? We are not putting rref and then inputting it. So if we are applying this function to that, we're calling this function on the matrix. Okay, so use the rref, reduce row echelon form function, okay? We call it on the matrix equation, and obviously we get that. But to get the first element in the output, okay? So you just put a 0 here, like to get the matrix format coming up, okay? And once you have it out, okay, so this is at the moment, I mean, if I go and say copy type, so it's a simpy matrix dot dense dot multiple dense matrix, whatever. It's a simpy formatted output, okay? And let's say once you've done this and you want it now back in form of a NumPy array, you just call, the NumPy array function. You use the NumPy array function to convert it back. So using the NumPy, using the np.array, let's say np.array function, yeah. And I would say that your basically simpy matrix goes here. So the simpy matrix, yeah. Okay, and that is it basically. So this was just a quick lecture on system of equations and how you would use Python to solve a system of equations if they have a solution. Okay, guys. Well, I hope you have enjoyed it, and definitely get practice, and I'll definitely recommend that if you don't know what the reduced row echelon form and the Gaussian eliminations are, you really need to, sort of read about it, at least have a sense of what this means, rather than just using the NumPy method that I just illustrated for you, you know, so that you have an understanding of what's happening under the bonnet. Well, thank you very much, and I'll see you in the next lecture.